research, and his research interests lie broadly in machine learning, with a recent focus on theoretical foundations of multi-agent reinforcement learning in games, deep learning, and uncertainty quantification. He's been doing some great work in that area. So today we're very excited to have him here to talk about the paper, When Can We Learn General Sum Markov Games with a Large Number of Players Sample Efficiently? Over to you.
Yeah, thanks, Chiara, and yeah, thanks for organizing this wonderful event, and thanks for having me here. So yeah, today I'll be talking about our work, when can we learn general sum Markov games with a large number of players sample efficiently. So this is joint work with my wonderful collaborators. So Ziang Song, who is an amazing undergraduate student at Peking University, I think still now, but he's joining Stanford for his PhD very soon. And Song Mei is at UC Berkeley. So let me click on this. So yeah, I guess as for motivations, there has been a lot of work on multi-agent reinforcement learning, solving hard AI challenges, and actually a lot of them involves like multi-agent IO with many players. So for example, poker, there's this six-player poker AI performing strongly against humans. And then like AI economists, they simulate some sort of economy using with many agents, and there's a government to set tax rates and everything, and then they can observe emergent behavior from this economy. And then emergent tool use, where agents play like hide and seek, and also StarCraft, which is obviously like a multiplayer game involving both team play and competition. And I guess at a high level, this whole thing is very interesting because this multi-agent reinforcement learning, of course, it involves the two big components. There's the sequential decision component that is there for our reinforcement learning problems, but then we additionally have this multi-agent part where there's more than one players and the environment. And then this is captured by the framework of Markov games, also known as stochastic games, where it is basically like a generalization, simultaneous generalization of sequential decision stuff in MDPs and also multi-agent games like in normal form games. And I'll talk about the setting in more detail later. And then here in Markov games, perhaps the most fundamental model is this two-player zero-sum Markov games, where basically you only have two players and they're in purely competitive relationships. So one player's gain is always the other player's loss. Like for example, when two players play like a game like Go. And so in this setting, perhaps the most natural kind of learning goal is to find a Nash equilibrium of the game, where which basically says each player will play the best response of their opponent, and there's only one opponent, right? And then there has been like a big growing body of work that says you can learn Nash equilibrium sample efficiently in two-player zero-sum Markov games. So this dates back to the classical paper of RMax in 2002, and there's a big line of recent work on that. However, much less is known when we think about more generally general sum Markov games with many players. Okay, so what is the challenge with the large number of players? What happens when you have a large number of players is basically you're starting to have something like this curse of multi-agents, which is that there are many players and each player can take their own action, right? And then if you look at their joint action space, which is like really the product space of each player's action space, that space is going to have like a size that is exponential in the number of players, because you just have like a product of each player's number of actions, right? So there's this thing really gets combinatorial, exponential number of players. And meanwhile, like an intertwined challenge is that like of course we want to learn efficiently from samples, right? Like we do in reinforcement learning, is we want to learn from bandit feedback or samples in practice, and this is also the case in practice. So we definitely want to understand this in theory too. So the question we ask in this paper is what equilibria can we learn can be learned in general sum Markov games with a large number of players, such that we only require polynomial number of players samples. Okay. Okay. Yeah, here is like a very brief overview of our main results. We basically show two kind of lines of results along this line. So we will first show that in general sum Markov games, learning correlated equilibria or its coarse version, coarse correlated equilibria, CECCE, can be done sample efficiently with polynomial number of players samples. And so this is our first result. And we also study Markov potential games. This is a special case of general sum Markov games. And in this setting, we can actually learn the Nash equilibria. We show how to do this and the sample complexity also polynomial in the number of players too. Okay. So any questions before I move on? Okay.
Yeah, I suppose you're gonna introduce this concept.
Of Markov games.
And Markov potential games and
yeah,
definitely.
Okay. Yeah. Okay, yeah. So so formally, so Markov games is this model that, as I said, generalizes both MDPs and normal form games, and this actually was originated earlier in the classical work of Shapley in the 1950s. And in this, specifically here, we consider like the finite horizon version of Markov games, and we let M denote the number of players. Here, this picture is only for two-player zero-sum Markov games, but the multiplayer general sum version is very similar, and I actually have it in mass over here. So so we're finite horizon, so we'll assume the game plays each episode of the game has H steps, capital H steps, so the game ends when you reach like SH+1. There's a state space of size S. So S1, S2 up to SH all belong to the state space. And importantly, for multiplayer Markov games, there's this action space, one action space for each player. So for ICE player, we use like script AI to denote this action space. And for example, for the first player, this A1, A2 up to AH belongs to this script A1. And I'll use AI to denote the size of this action space. Okay, so what happens when you are at a state is that each player will play an action. So since I have M players, the actions will be like A1H up to AMH. And after all players play their actions, and then they do this simultaneous, there's no like turn-based thing. And I assume like they all play only based on SH, and then the actions play simultaneously. They cannot observe like each other's action before they all play. And then this is the simultaneous setting. Of course, this is also a generalization of like the turn-based setting, etc. And after all this happens, now each player will receive their own reward. So I'll use Ri to denote the reward for the ICE player. Since we're in general sum setting, the Ri not necessarily have any relationship across the ICE. So just some general RIH of the state and the joint action. Right, and then finally, after this, we'll have the transition. The transition is similar to MDP or two-player Markov games, as you transit from the state and the joint action to your next state, and this happens in the Markov fashion. Okay. With this setup, we can now talk about policies and values, etc. So we'll begin by looking at Markov, like a special case of the policies, which is like a Markovian and product policy. So so with a Markovian product policy is that like the players will play their actions independently, conditional on SH. And each player's own policy is also like a Markovian policy, so not history dependent, only depending on the current state. And then that will give a policy like this. So so at SH, the ICE player's action AIH will be sampled from pi IH of which is a probability distribution over AI, and that is conditioned on the SH. So this will be the policy for the ICE player, and you collect them all together. This will give the policy of like the joint policy of all players. And this will be a product policy because players act independently, like the ice player does not affect like some other Jace player. And we can define the total cumulative reward, expected cumulative reward, which I also call gain value for the ice player. This is just like in expectation, the cumulative reward of RIH, the summation over little h. So note that each player has their own VI. And then, so formally, we can now define the Nash equilibrium as, when you say a product policy pi is an epsilon approximate Nash equilibrium if this any gap is less than epsilon. And where this any gap is, I look at what is the maximum gain of the ice player by changing their own policy. So I can change, so I start with some product policy pi, right? And I keep other players' policies fixed. I look at what is their own best pi I dagger, and this is the gap they can gain, right? This is not negative, and I take the max over all players as well. So I say when this is less than epsilon, I say pi is an epsilon approximate Nash equilibrium. So yeah, each player plays the, I guess, approximate best response of all other players' policies. Okay, so what do we know about learning Nash equilibrium in Markov games? And perhaps it is good to take a step back to think about the normal form games, which is really a special case of general Markov games with just one state and no horizon as well. So s equals 1 and h equals 1. What do we know about learning Nash equilibrium in multiplayer normal form games? Right. So if we think about this a little bit, the naive approach for learning Nash equilibrium requires this product of AI over epsilon square samples, right? And why is that? Is simply because like you can view it as like as a big bandit problem over the joint action set, and the joint action set has like this many actions, right? Product of AI, and you try each action 1 over epsilon square times. Like think about pure exploration setting. You try each action 1 over epsilon square times, and you get it epsilon accurate, and you can output just the one Nash equilibrium of that empirical game matrix or tensor or whatever, right? So that one definitely works, but it requires exponentially many samples. But unfortunately, it's the case that this is also unavoidable. So it's shown in a line of work, in particular by Rubinstein in 2016, that where really he shows that finding an epsilon, like epsilon 0 Nash equilibrium in multiplayer NFG normal form games with only 2 actions already requires like exponentially in M payoff queries, and this happens even if the payoff queries is noiseless, and this error tolerance epsilon 0 is just order 1. So even in this kind of favorable setting, you still require like exponential in M. So at least exponential in M is kind of unavoidable for learning Nash equilibrium. And since this happens with in normal form games, this as a special case of general sum Markov games, then it seems like at least for learning ME, this exponential in M is unavoidable. And I'll just remark here that this is kind of different from the pipette hardness of computing Nash equilibrium in general sum games. For example, of the line of work by Daskalakis et al. Because this hardness is information theoretic. It doesn't say anything about computation. It rather says your query complexity has this lower bound. Whereas this pipette hardness is like you fully know the game, but you care about the computational complexity. So these are like different things, and not to be confused. Okay. All right. So with the hardness of Nash equilibrium, we'll seek alternatives, right? And then in normal form games, there's like a natural alternative called coarse correlated equilibria, CCE. Is defined as follows. So basically, the definition is very similar as a Nash equilibrium, except that now I'm defining a CCE to be a correlated policy path, right? So recall, with Nash equilibrium, the policy has to be a product policy, right? Because each player is already playing the other player's best response, and here the situation is a bit different. So so now a CCE is defined a correlated policy. So pi is a correlated policy where players can like act in a correlated fashion. So you can think about like for normal form games, you can think about like an action distribution on the whole big joint action space instead of like each player having a probability distribution over their own space. And the CCE is asking that for this correlated policy, no player has epsilon gain in deviating from that correlated play. And when they deviate from the correlated play, we ask them to like play independently, like they cannot utilize the correlation in any way. They must play their own pi dagger and use their own randomness. So yeah, so this is a generalization of Nash equilibrium to correlated policies. And it is a standard result in, I guess, online learning and games literature that CCE in normal form games can be learned by just putting a lot of putting no regret algorithms for each player together. So if you let, so for any normal form game A, you let all players run some no regret algorithm, learning algorithm against each other for key rounds. And then you say at the end of the play, you output this pi hat, which is just the simple mixture of the joint policies played in the all capital T rounds. So each of these pi t is a product policy, but this pi hat is a correlated policy, right? And then this one satisfies low CCE gap as long as each of the regrets is sublinear in T. So if each of the regrets is little of T, then this is little of 1 in terms of T. And then further, this generalizes to the bandit feedback setting as well, right? Because we know how to minimize the regret when you only have bandit feedback. So if you let each player run an adversarial bandit algorithm, such as EXP3, you get like square root AIT regret, right? So you put into this, you get like the CCE gap is bounded by square root max AI over T. And so this is nice because so to let this right-hand side be bounded by epsilon, you only need like T scale as max AI over epsilon square, right? So this kind of avoids the curse of multi-agent because the sample complexity only depends on the max of AI instead of the product. So for normal form games, there's this, sorry, I think Chaba has a question.
Sure, just finish the sentence. I will ask my question after you finish.
Oh, okay, okay. Oh yeah. So the sample complexity depends on the max AI, whereas like any depends on product of AI. So there's this nice separation in normal form games. Yeah.
So my question is there a nice intuitive explanation of the difference? So we see that there are striking differences in terms of the complexity, either information theory or computational or complexity of getting an epsilon Nash versus an epsilon CCE. But should we be happy with a CCE? Like what's kind of the intuition there, right? So Nash is kind of like really defensive and it's like emphasizes independence of each of the entities. So they are not synchronizing with any ways. So what are the situations where we are also happy with a CCE type of equilibrium?
Yeah, I mean, that's a good question. I think like I think for general sum games, I don't really know of a good answer. I think even probably you can argue even like the Nash is not sometimes like desired. Like for example, if you think about like the poker application, right? And then the Nash is really like a solution concept of like if you have 6-player poker, right? The Nash is really a solution concept of say like 5 players. I can say like this product policy of that other 5 players. Like given like I fix the policy of all other 5 players, then I can say, oh, my policy does the best against this. But this doesn't work if the other 5 players starts to like correlate a bit. And so like CCE is kind of like one remedy to that is to say like I fix a correlated policy. And this is unlikely in 2-player zero-sum games where Nash is also min max and max min, right? And you can say like I play Nash and I'm safe. I earn like a non-negative expected reward, everything. Yeah, so CCE is like one remedy to that is to say like I allow players to correlate, and then like in that case no player has the motivation to deviate, but still whether that like players correlate really happens in reality is like a question, I think.
Yeah, so maybe one can also think about, like, in terms of applications, whether there you expect competition between the agents, or you expect cooperation between the agents. Like, okay, every agent is interesting, kind of like maybe maximizing their own reward, but maybe I don't know. It feels to me that just the fact that you're willing to synchronize with the other players somehow makes this a little bit more cooperative, the CC, than the Nash. Maybe
Yeah, it's definitely cooperative in the sense of like sharing randomness, everything.
yeah, it's like you have to kind of, but in Nash as well, you have to agree on which Nash equilibrium playing. If I don't know. So how to think about, like, which equilibrium concept is suitable for a given setting?
Yeah, I think I kind of view this at least myself, I kind of view this kind as kind of like an open question, or like a motivating question for things. I think in reality, in a lot of like real world multi-agent problems, like I think people just run like independent policy optimization algorithms similar to no regret algorithm, right? And then they put them together, and they don't even use it in a CCE way. They just say like I just like perhaps like they can do like averaging within each individual player, but they don't do this correlated averaging. I'm thinking about like for example poker applications. I think like people talk about like this using it in a kind of like a Nash way, or even just evaluating its performance in reality, like works well, but they don't really understand. Like that's definitely not a CCE, and perhaps not a Nash because of the computational hardness. So what is that is like not understood yet. But yeah, I think CCE.
Is there any connection to really cooperative games where you would, like you just maybe are interested in scaling up things, and then you want each agent to do its own thing, to do its own optimization, and yet you want the agents to cooperate to, I don't know, maximize some social welfare. So I was wondering whether the CC concept is a better fit for that setting than, for example.
I'm not sure. I think CC is still for like it's still kind of competitive in the like, even though they correlate, but it's still kind of like competitive.
Yeah,
a bit competitive in nature, right? Like no player has the game to deviate and stuff. Like you cannot leave the team play. I don't know. I guess
I was wondering whether this has some favorable side effect in these other settings where you have extra structure. But anyways, like we can take it offline. It's getting too far.
No, I agree. Like if the game has structures, then perhaps you can further study. Like in these games, CC is also CC also has some additional properties, and that can be nice.
Okay.
Yeah. Okay. All right. So yeah, and then given this like nice complexity result, the normal form games, of course, we want to generalize this to Markov games, right? But and then in Markov games, the definition is pretty much the same. Like it's the same equation, but here VI means like the value in Markov games, but otherwise the equation is the same. But then there are challenges, of course. In like because of reinforcement learning, of course, we want to ensure efficient exploration. We want the algorithm to visit all relevant states, right? And also there's this subtle point is that getting no regret in Markov games and under bandit feedback is kind of challenging. And I think at the time of that work, we were not fully aware of this picture, but there's this nice recent work by Liu Wang and Jin, who says getting no regret in Markov games from bandit feedback is like challenging unless you have some additional feedback about the opponent's policies, etc. And but yeah, the question is that like since it's perhaps we could not expect like a straightforward generalization of the no regret to CCE conversion that holds in normal form games to also hold here in Markov games. So and then the question is what's the right goal or algorithm design? And also side quest is like we all want a decentralized algorithm. We don't want an algorithm to maintain like a big Q table that has exponential size. So how do we do that? And fortunately, these questions were all addressed in the more basic setting of two-player zero-sum Markov games in the Nash relearning algorithm. So we'll look at that and hopefully take some inspirations. So the Nash relearning algorithm is an algorithm for two-player zero-sum Markov games, and here I describe it for the max player. It's a decentralized algorithm, so I only need to describe it for the max player, and the other side is symmetric. So in the first step of this algorithm, it maintains an optimistic v-values, and it uses incremental update to update it, similar as in Q-learning. So this is the update for the v-values. So each time a state is visited, you take some learning rate alpha t to update it a little bit, and the update is to use the observed reward plus the actually observed next state as h plus 1. And then you use bootstrapping, right? You use like the optimistic v-value of h plus 1 step, and you add some exploration bonus. So the structure is pretty similar to Q-learning, except that I update the v instead of updating the q. Right, and the bonus ensures exploration. And then my next step is to update my policy based on the v, right? Since I don't have a q, I don't have a guidance for policy by greedy. So I need to maintain a policy. And this policy, I update it by some adversarial bandit algorithm. And so each time I visit SH, right, I must have played some AH, right? And I observe a bandit feedback of the loss. I plug this guy, which is basically like a scaled and flipped version of this thing, R plus VH plus 1. I put this guy into the adversarial bandit, and I say like playing AH gives me this loss. I will update my adversarial bandit algorithm with this bandit feedback. Okay, so and then you can use any adversarial bandit algorithm here in principle, but you need to ensure some, for example, some weighted regret or anytime regret guarantee. And we use weighted anytime FTRL to do that. And the good thing about this adversarial bandit algorithm is that it achieves like a certain per state regret. So with respect to this loss function, the mules will achieve regret, and then this regret, you have one regret at each state, right? And then after all this is done, you can play a new episode with your policy and observe your trajectories of transitions and rewards. And after the whole thing is done, you output this what we call the certified policy mu hat. And I will not go into detail about that at this moment, but just to keep in mind, this is like a history-dependent policy that is like non-Markovian. And then what we can show in that paper is that Nash v-learning achieves like a low Nash equilibrium gap within this many episodes of play, and know that here the dependence on the action space is only like the max of them instead of the product. And so yeah, so this protocol is nice, and it turns out this can be generalized quite directly for general sum Markov games and learning CCE. And the algorithm design is entirely parallel, right? So I can still maintain my optimistic v-value, one for each player. And each player can deploy their own adversarial bandit subroutine to get their policy, pi I. And the player will play an episode with the policy pi I. Note that here, the player does not need to know the opponent's policies, and that this can all act in a decentralized fashion. The player maintains their own policy pi I, and they observe their own transitions and rewards, not even necessarily observing other players' actions. And after k episodes, you output a certified correlated policy pi hat. And this is what we show. So this algorithm, CCE v-learning, achieves learns if to approximate CCE within this many episodes of play. So this is very similar as the Nash v-learning, except that I replace the max A1, A2 by the max of all the AIs, right? And then this is nice because it avoids the curse of multi-agent, right? You only scale as the max of AI instead of the product. So this is similar as in normal form game, learning the CCE in normal form games. Okay, so I have some discussion about this result here. So as I said, it avoids the curse of dimensionality, scales only with respect to the max of the action space. And yeah, it learns in the online exploration setting from samples. And it is a decentralized algorithm. What's not so nice about this is that the output policy is non-Markovian. So this pi hat is this certified correlated policy is has some history dependent component in it. So it's not a Markov policy. But some other stuff is known about learning Markov policies. So if you really want a Markovian CCE, meaning that the correlation only happens at each state, but from state to state, it's really Markovian. It does not look at histories. Then this can be done. You can use like a value iteration type algorithms to do that. But the sample complexity there had to scale with like the product of the action space. And then so here I'm only highlighting the dependence on AI, and also further in the talk I'll probably do that frequently. So product for AI over epsilon square. You can learn the Markovian CCE, and then there the algorithm really is like a dynamical programming style. So that's why you can do Markovian CCE.
Can I ask a quick question?
Yeah.
For the basic result and the algorithm. So what is the correlation? Like, how is the correlation introduced in the algorithm? Like, are these agents really?
I haven't put it here. Like you think about normal form games where the correlation is introduced by like a mixture between like the T episodes, right? Here it's similar, but it's like a more subtle, like a nested mixture. So this is not a simple mixture of outliers policy. This is really like some sort of nested mixture where at the first step, before the first step, you sample like a random bit, and then they play according to this random bit, and then they transit to the second state. And then there you need to sample random bit again. And then the random bit is like based on the state. So say if you transit to some S2, then you sample a random bit, and the policy you use at S2 depends on like what the S2 is and the random bit. So it's kind of like a nested mixture of Markovian policies that is like altogether very non-Markovian. Yeah. Yeah, I have a backup slides about what the certified policy is, but
okay,
I guess
I'd be curious. Thanks.
Yeah. Okay. And I also mentioned in passing, like there's very recent work by Dasklakis, Golovich, and Zhang, who like also proposed a new algorithm for learning Markovian CCE in general sum games, and then their sample complexity scales as like max AI over epsilon cube. So this is nice because like it learns Markovian CCE and it's max over AI, but with slightly worse epsilon dependence. And of course, the open question with Markovian CCE is like how do we improve upon either? Okay. So I guess in the interest of time, I'll probably go through this part pretty fast. It's like we can generalize all these CCE results to correlated equilibria. And in normal form games, there's this nice connection tool between swap regret and correlated equilibria. And so swap regret is like a stronger notion of regret than the usual, like called external regrets. And you can put no swap regret algorithms together to learn CE. And specifically, you can combine the swap to external reduction with EXP3 algorithm to get like square root AI square T swap regret for the IS player. And just by modifying the CCE learning algorithm for just by modifying the adversarial bandit subroutine to this no swap regret algorithm, we can get this CE learning algorithm who learns epsilon approximate CE within this many episodes. And then this is only like one H factor larger than the one H factor and one max AI factor. And the max AI comes from the you needing to minimize the swap regret. Okay. So I have a brief literature note here. So this is our paper containing the CE results, and there are two other very concurrent papers. So the paper relearning by Jian et al. They also basically have the kind of same CE results, and in particular their CE rate is better by a factor of H, and this is due to their using a different swap regret minimization algorithm from ours. And there's this other paper by Mao and Basar. They also have like a very similar, pretty much the same CCE result. And all 3 papers are based on the relearning algorithm proposed in this our previous paper, near-optimal reinforcement learning with self-play, which did this for 2-player zero-sum Markov games. Okay. All right. Sorry. So any questions before I move on? Okay. Yeah. So so now I'll talk about Markov potential games. So this is really like a collaborative type of general sum Markov games, right? So the definition is over here. So a general sum Markov game is a Markov potential game if you have this kind of like potential structure. So take the difference between the ice player's reward for any policy where you only change the ice player's policy from pi I to pi I prime and hold all other players' policies fixed pi minus I, right? Then you get this. So the right-hand side is something that does not depend on I, right? You have some universal potential function phi for all players, and this value difference is also exactly the difference of the phi function of the same arguments. So really, it says like any performance improvement is independent of the index I. It's just like the difference in some universal potential function. Okay, and then here's a numerical example. I have like a 2-player general sum Markov game, and you can verify this is a potential game with the potential function on the right-hand side. Like for example, you take like you take like player 1, you compare 2 actions like 2 versus 0, right? This is also the difference between 2 and 0. You take the difference between 3 and 0. This is also the difference between 4 and 1, right? And so on and so forth. You can check this is a potential game. And a very important special case is, of course, cooperative games where every player has the same reward, right? Because obviously you can then take the potential to be just the reward of all the players. And yeah, it's an important special case in practice as well. You often need to solve cooperative games, but with a lot of agents. Okay, so let's go back to investigating the learning Nash equilibrium in Markov potential games. Okay, so let's think about it a bit. So learning Nash equilibrium in Markov potential games is kind of similar as a coordinate-wise local max structure, where it's really like just the local max is in terms of flipping one single coordinate, right? So why is that? This is because if you take the definition of the Nash equilibrium, which asks this left-hand side to be non-negative, for any pi to be an NE, right? You ask this for any pi I prime to be non-negative, right? You ask it to be not having any gain. But by potential game definition, I can just write this as like the potential function between of pi minus this guy, right? And I ask this to hold for all coordinates I, right? And that means I cannot increase phi by flipping one coordinate to some other pi I prime. But I don't restrict myself to flipping like 2 or more coordinates. If I flip 2 coordinates together, then it may increase, and that I don't care. So Nash equilibrium only cares about local max with flipping at most 1 coordinate. And importantly, this is not to be confused with the global max, where you can flip all coordinates together and you ask the phi to not increase. And this is much more challenging because basically you need to enumerate the whole game matrix, etc. So whereas the Nash equilibrium is perhaps much more tractable, right? And to learn this Nash equilibrium or coordinate-wise local max, there's a very intuitive coordinate ascent algorithm, right? And then we can illustrate this in normal form case. It's very simple. Basically, start from any combination of the actions, enumerate all this kind of single coordinate change. So for example, here I try to go along the x-axis and I try to go along the y-axis. I look at which one gives me the maximum gain, and then I jump to that point and then repeat the same. This time I necessarily move along another direction because along that direction I'm already the max. So I move along another direction. I repeat until I reach some terminal point, some fixed point, and in that case I'm already at the Nash equilibrium. And it turns out that this algorithm can be directly generalized to learning Markov potential games with reinforcement learning. We show that there exists an algorithm, Nash CA, Nash coordinate ascent, that finds an epsilon approximate NE of a Markov potential game within this many episodes of play. Okay. So let me show you the algorithm real quick. It's very simple. In each step, I just do exactly almost the same as this coordinate descent picture I just showed you. So let each player fix the opponent's policies and run some single agent reinforcement learning algorithm. For example, UCBVI, whatever gives you the Sharpe rate for a good number of episodes that gives you like epsilon or like 0.01 times epsilon suboptimality, like near optimality. And then that gives you a new policy pi I hat. And along the way, you may also get some value estimate of that policy, right? Pi I hat combined with the opponent's pi negative I. In the second step, I compute the estimated maximum improvement, which is I just take this and contrast it with the policy I began with. So take the estimation of the difference between the two policies. And specifically, I also need to maximize this over the index I. So I find the player that gives me the maximum gain, and I call that I star. I call the maximum gain delta. And then if delta is greater than epsilon over 2, then I claim I must have at least the order of epsilon gain. Then I update my pi to this new policy where I change this one coordinate to the pi hat of I star, the improved version, and I repeat the go to step 1. But otherwise, if delta is not greater than epsilon over 2, then statistically, I'm already at like an epsilon Nash with high probability. So I stop here and I return the policy pi. All right. And then there's a one-line proof sketch of this algorithm. If you assume the single agent reinforcement learning result, is this claim that the Nash CA will terminate in at most 5 max over epsilon rounds, right? Because assuming all concentration holds, each round will improve the will increase the potential function by at least say epsilon over 4 or something. And then the algorithm must terminate within this many rounds. And then you multiply this by this number of episodes over here, gives you the 0. Okay. I'll talk about some related results for Markov potential games here. So note that here, there's also a wise curse of multi-agents, right? Because you have summation of AI instead of like the product. And you have additional 5 max here, but this one in Markov potential games, this emits like a trivial bound of m times h because it's just a contrast of all the players' total rewards. So there's this, you can use the Nash VI algorithm, which does not utilize the Markov potential game structure at all to also learn results to also learn the Nash equilibrium for Markov potential game, but there you need to pay product of AI because it is like, it does not utilize the potential structure. You can also use policy gradient algorithms. And these people, they establish this nice like landscape property of policy gradient algorithms in potential games. And this can be turned into an algorithm for the sampled case. But just as typical with other policy gradient approaches, it admits like a worse epsilon dependence, for example, 1 over epsilon to the 6. And also it requires a distribution mismatch coefficient and does not handle the exploration by default. Right. And we also show a lower bound for finding pure strategy Nash equilibrium. Note that we can learn a pure strategy Nash equilibrium with our upper bound. And we have a lower bound, which is summation of AI over epsilon squared. And this is a slight improvement over the naive one by putting like single player games together, which is which will give you max AI over epsilon squared. And then, so contrasting this with these upper bounds, there's an open question of whether summation of AI or even max AI or epsilon square upper bound is achievable, which will be the best of both worlds because our Nash CA algorithm, because of this two-layer structure, two-level structure, you have 1 over epsilon iterations in the outer loop. It gives you 1 over epsilon cube iterations. And the Nash VI does have 1 over epsilon square, but it needs to pay the product of AI, right? So this doesn't seem too natural, at least to me. And I guess the open question is, can you achieve the best of both worlds, summation AI over epsilon square? Okay. Yeah. So yeah, I'll summarize our results here. So for general multiplayer general sum Markov games. The existing lower bound even for normal form games already show the exponentially in M lower bound, sample complexity lower bound. And in this paper, we show upper bounds for learning CCE and CE, and both is only polynomial in the max actions. And we also identify Markov potential games and design algorithm with this sample complexity. And for learning C and CC and Markov games, Markov potential games, this already implied by the above, because it's a special case of general sum Markov games. And then this is these generalize our the previous results in zero sum games where you know all three, because you can do Nash equilibrium, you can do all three with max A1, A2 sample complexity. Okay. Yeah, I guess I'll probably go to my last slide here, and then I can take questions. So yeah, so in this paper we study like what kind of equilibria are learnable with polynomially many samples and number of players, and then we identify two cases: learning C, CC in general sum Markov games, any general sum Markov game, and learning Nash equilibrium in Markov potential games. And there are a number of future directions. For example, our rates are probably not tight. In CECC, we're probably not tight in age compared with like single agent reinforcement learning. And how do we do that? In Markov potential game, we're not tight in epsilon, or you can say the Nash VI approach is not tight in AI dependency. How do we improve upon either one? And also for our algorithm for learning CECC, we really require to output this kind of non-Markovian output policy. And how do you? And then there are more recent approaches that consider like Markovian output policies, right? Like how to even further improve the algorithms there, get better rates. And then yeah, of course we haven't touched upon function approximation. Everything here is tabular. How do we do function approximation for general sum Markov games? And finally, besides NE, CE, CCE, what are the other equilibria that make sense and are learnable? And for example, like Stackelberg equilibria that has like a rather different structure, or perhaps some even new definition of equilibria. Like how can we go beyond all these? Yeah, so I'll conclude here, and our paper, the link to our paper is here. And yeah, thank you for your attention.
Thank you. Gary has a question. Gary, do you want to ask a question?
Yeah, I'm reading it. I can see it. One question I was going to ask is if your bound depends on some kind of distribution mismatch coefficient or smallest visitation probability. Yeah, you don't. Given your discussion of related results, you don't seem to have such factors. Could you say a few more words about this? Reduce this, and then he also said this typically appear in analysis that rely on reducing the global regrandization problem to local regrandization. Okay, I can switch to that, jump to that slide. Yeah, so we don't have distribution mismatch coefficient, and I guess here for Markov potential games, the reason is that we just reduce it to single agent reinforcement learning. Like basically think of our algorithm just as like an instantiation of this coordinate ascent kind of picture into reinforcement learning, where each of this line is replaced by single agent reinforcement learning algorithm. And then that because single like UCBVI can handle exploration, so does the overall algorithm, which just does this for all players. So in Markov potential games, that's the reason why we don't pay the distribution mismatch coefficient. But here we don't rely on reducing the global regressionization to local. This is just a reduction from many players to one player. And before in the CECE thing, here we also don't pay the distribution mismatch coefficient, and this is because our algorithm incorporates optimism to handle the exploration. Yeah, I guess I can jump to the algorithm, like because of, sorry, this is not read. The CECC version is here. Yeah, because we maintain optimistic V values, and you can show this is indeed like optimistic with respect to like certain best response policies of the certified thing. Like this is indeed optimistic greater than the best response, like some kind of like a V dagger value functions, like which is like the best response of your certified policy. You can show this is greater than that, and the playing with respect to this guy ensures you do exploration. and thus you don't need to pay the like whatever like by combining per state to overall. Yeah.
So here the bonus depends on some global information. I guess like that's fair because like the state information is shared between the agents. So you're kind of like counting how many times you have seen various things, right? But it doesn't depend on like how many times different actions are used.
Right,
it
right.
only depends on state visitation counts, right?
Right. Exactly. You're exactly right. Like because this is on V, the bonus is taken like the T is the number of like visitation to the state only. Like there's no action here, and yeah, like it's not counting like the number of like the visitation count of SA is just the visitation count of S.
So could it be that the higher price for the horizon is because you're using state value functions instead of action value functions and bonuses that depend on states?
Kind of, yeah. I would say kind of, yeah. So the higher price in terms of the horizon here, H5 instead of like H cube, is like it's because like it kind of originates from the regret. Like typically with optimism, you only need to bound like the concentration, right? Like the optimism is to account for the uncertainty in like the reward and the next stage transition, etc. And so you only need to design your optimistic bonus to cover your concentration. But here, the optimistic bonus need to cover both concentration and the regret of the adversarial bandit. Like you need to show, like roughly speaking, you need to show like bonus is greater than the thing plus bonus is greater than both the concentration term and the regret of the adversarial bandit. And because we don't have that fine-grained, and then back in the single agent IL, typically you reduce the state dependence by like careful analysis of like the concentration factor, for example, Bernstein, and also like the concentration of the transition probabilities, right? But then here, since it needs to cover both things, you need to make both things super tight. You not only need to introduce Bernstein bonus, etc., and you also need the regret to match that, like the horizon dependence incurred by the regret of the adversarial bandit to also match the tightness of the Bernstein bonus or whatever. So that makes it challenging, and we didn't know how to do that. So we instead, because of the regret, is much larger, and we instead to just use the Hofting bonus as well, the simpler Hofting bonus as well, and then like that incurs higher. The combination of both incurs higher H dependence.
I see. Interesting. I do have a very different question, but other people are thinking about questions. So for these Markov potential games, it seems that they are really ideally suited for, in general, the potential structure is ideally suited for this coordinate ascent type of search algorithms. Is there an equivalence, like whenever coordinate ascent works, no matter where you're starting, is it true that like you have a potential game? Let's say you just have normal form games. It's probably
yeah, that's a good question. You're asking like the converse, right? Suppose.
Yeah. Probably not true.
Yeah, like this. Yeah.
Yeah. It's like if you granted coordinate ascent succeeds no matter where you're starting, is it true that you can always find a potential function, or is there something more general, or like, yeah, like what is the relation between these two sets of games? And if it's more general, if coordinate ascent succeeds more often than just in potential games, granted to succeed no matter where you study it, then why would you study potential games? Why not study just games that are ideal for coordinate ascent?
Yeah. 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 I don't know. Yeah, that's a good question. Yeah, I think. Yeah.
It won't work for everyone. Okay. So we don't know the answer.
Yeah. Yeah, we probably don't know. I guess, yeah, I kind of view when I started learn about this potential game maps, I felt it's natural because of like really just this cooperative setting, like just cooperative games, but you cannot learn the global max because then there's no structure at all, right? And then so you say you learn Nash, and then it's like it can be done by coordinate descent. So it seems natural. But yeah, and then potential games is perhaps like slightly more general than that. But yeah, what is a broader class?
So regarding this cooperative aspect, if there was only one reward function that all agents are trying to jointly maximize, I guess maybe one of the challenges would be to somehow decompose it into reward functions for each of the agents. But the simplest decomposition would be that like every one of them just gets the same reward function. So if the rewards are identical in a way, right? Like for all the agents.
Yeah. I mean, in correlated games, yes, the rewards are identical.
Yeah. That doesn't necessarily make the game a potential game.
No, if you're really the rewards are identical, then yes, it does make it a potential game, because
So
the
then
potential is just a reward.
definitely a potential game.
Sorry.
Okay. Oh yeah. Oh, absolutely. Trivial. It flows directly from the definition. I see. So that's why you say that it's ideally suited for cooperative situations, because yeah, if you have this cooperation, the desire to build agents that cooperate, you can just treat this potential game, and you can solve it with coordinate descent. Well, that's nice. Cool.
Yeah, I kind of really see it as like just a generalization of cooperative games, but you cannot afford to find a global max, right? Because of like combinatorial structure. So yeah, you and then you agree on some weaker solution concept, which is like naturally the Nash equilibrium for potential games.
Right.
Yeah.
So what was the result for again for the potential games, like sample complexity?
Let me jump to it. It's this.
So
It's
phi matrix epsilon cube. Okay.
Yeah. So
right.
so there's this epsilon cube. Yeah.
Do we have an idea about lower bounds?
Yeah, I mean, like there's the single agent IR lower bound applies. So H cube SA over epsilon square, and then you can take the max over AI. And so here we were not that happy about max AI. We thought since the upper bound is summation of AI, we really try to at least nail down that. And then it turns out that is true. Like you can actually do a summation AI or epsilon square, but this lower bound does not have S. And the H is also not tight. I think we have like a H squared or something out of all the H's. But here the emphasis here is like the AI dependence. Like you really need to depend on the summation of AI.
Yeah. Well, that sort of makes sense. So you think that the epsilon cube is real or it's not real?
I don't know. I mean, like it's avoidable if you afford this product of AI. So right now the best.
No. You can't.
It's a summation of AI.
The summation of AI is an absolute bound.
Yeah, then I'm really not sure. I think.
Okay.
Yeah, I think this is open. Yeah.
And you have also phi max, which can be as large as m times h. So ultimately that would be h to the power of 4.
Yeah.
Cool. Yeah. Nice questions here. Mm. Interesting. But in a way, yeah, like this summing over the size of the action sets really brings out the price of, okay, it doesn't quite, but like brings out some aspect of the price of having multiple agents doing the same thing.
Exactly. Like yeah, because yeah, the summation of AI from the upper bound, the summation of AI is exactly like, because here the step one really needs to be run by all agents at each round. So each round you don't pay just one of this, you pay like all of this. So you get summation of AI. Yeah, and then also like another criticism here is like it is not a decentralized algorithm, so to speak, because you need to run this for agent one first, and then agent two, and up to agent M, and then this is not a very natural decentralized. Perhaps like it's more fair to say this is centralized. And after that, you make improvement on one player only, and all other stuff are like discarded. So yeah, but you do need to pay the summation of AI by this approach.
Uh-huh. So what would be in this decentralized case, what the shared information would be just state?
Yeah, that's a good question as well. I don't know of like any formal. I don't think there's a formal definition, but yeah, for example, the CCEV learning, you can think of it like comfortably. I'm thinking about it comfortably as a decentralized algorithm, because yeah, for each agent, it only sees the SH, the own action they play, the AI age, but this algorithm does not require like observing the other agents' actions and rewards. So only their own AIH, RIH, and yeah.
Okay. Yeah. So you said that you have this extra slide about this certified correlated policy.
Oh yeah.
How is that?
It's just good time to do that.
Right.
Oops, sorry. Sorry, I think my slide just died. Let me reshare it. Yeah, so here's the certified policy. Yeah, I guess I it's probably needs like I can probably explain it. So so usually with like recall in the normal form game CCE, right, the correlation, the correlated policy correlation is induced by the random bit in the sampling K, right? Like you sample K uniformly from the number of episodes, then you play the product policy indexed by K. And then here the complicacy is in like the K is not just sampled one shot, it's updated along your play. So while you play in an episode for step H, little h from 1 to capital H, this K is actually like a moving thing. So you first at the first line you sample a K uniformly from K, but then depending on which state you're actually in, you're going to like take the value of T, which is the visitation count of that state prior to the K's episode. So say if K is 100, then you have and then you have visited 10 times, then then T is 10, and you further sample a number from this 1 to 10. So you sample an L from this 1 to 10 with the probability equal to like the weightings induced by your learning rate. So the alpha TJs, and then you update K to be, so say if your L is like 5, then you update K to be like to be the fifth visitation, like to be the index of your fifth visitation, not your 10th visitation. So K moves a bit smaller, and then you use that K to play the current step, and the next step you repeat. So next step K gets even smaller, T perhaps gets smaller I guess at a high level because you move to a different SH, but
Mhm.
but the K definitely, yeah, but the K will typically get smaller and smaller along the play, and within each step you use K to induce the correlation, but the K changes.
Yeah, sure.
Yeah.
Oh, okay, pretty complicated. So what's the intuition behind this?
The intuition is that like we really we really need to ensure the valid optimism. Like we didn't know before we designed this, we didn't know, like for example in Nash relearning, what is like you can design like the optimistic pessimistic version of me, right? But we didn't really know what that covers besides the Nash value. And covering the Nash, like bounding the Nash value is not enough. And the design of this policy is to give a policy whose value is falls below the optimism, like whose value is bounded by the optimism. And in order to do that, we need this policy to somehow like imitate the behavior of the optimistic like incremental update structure of the V's or the Q's. Like think about in Q learning, right? Like your Q value is like it's a weighted average of historic Q values, historic optimistic Q values. Here's the same is the historic average of the V values. But then in order for that to be for this kind of V value to be an upper bound of some policy's performance, we then design the policy to have the same structure, like nested mixture with the same set of weightings, so that the policy policies is like they're also taking this nested mixture with the same structure as the value update itself. So basically, if you write it down in math, it's like it's like the V upper bar and the value of the certified policy has the same kind of recursive structure. Then by optimistic bonus, you can show like recursively the V upper bar is like a upper bound of this policy's value. And that's how this policy was originally designed.
Right. I guess it's a pretty important component as well that this policy should bring in reward close to what the reward was brought in during learning, because otherwise you can propose many policies that are
exactly
below the optimistic value, but okay.
At very high level, it's similar as the CCE in normal form games. Is like you want your output policy to achieve reward similar to the reward you have seen during learning. Like, and then in normal form games, this is done by naive averaging of joint policy, because then it's like exactly the same. The structure is exactly the same as the no regret guarantee, right? Like because your PT competes with the LT, which involves the opponent's policy in the T's round, and here it's a super high level. It's the same thing. Like we want the policy to achieve rewards close to like exactly what we have seen during the learning, and we want.
And why is it simple to explain why the naive approach doesn't work here?
Because at that time, before we didn't know the hardness. I think at least at that time while working on upper bounds, this is because we didn't really know how to design like no regret algorithm for Markov games. Like we only know how to do it per state, and so we kind of pretty much began to seek like how to combine the per state. We didn't have any idea how to do it for the entire like Markov game directly.
I see.
But this is I guess that claim is pretty much in hindsight, because now we know the hardness. But at that time we didn't know the hardness. We just we probably didn't try to think about the upper bound too hard, but really like we have no idea how to do that. So we instead look at this, how do we extend the like Q learning for a single agent case to the two agent case. And there the natural thing to come up is the like minimize the per state regret if you only have the V instead of the Q.
So what is the hardness result that you're referring to here?
I think this is a recent paper by Qinghua and Qi and Yuan Hao. Where is that? So I think they showed like if you want to do no regret in Markov games against adversarial opponents, then you can easily define a hard instance of the game and the adversarial opponent such that, and then you only observe bandit feedback such that it is challenging, I think, at least like exponential in the horizon or something like
Okay.
Yeah. And then I think they have like a bunch of positive results under additional assumptions like you like the opponent's review policies at the end of each episode. Like you not only you see bandit feedback of your trajectories as prime reward, you also see like what is the opponent's policy at the end of each episode. But of course you don't see the MDP. If you see the MDP, you're done. Yeah, you don't see the MDP, you see opponent's policy. Then you can do some positive results. Yeah.
Okay. So it's really the lack of information. Well, okay, that makes sense. Okay, cool.